Now here we go. I'm going to show you a phase diagram, and then I'm going to show you a process in the phase diagram, and then I want you to determine the delta E versus temperature diagram corresponding to that process. All right, here we go. 1 minute, maybe 2. You can still discuss with each other. That's the goal, okay, to collaborate. And then if you want 1, and here are our responses. Look at that. Okay. More than 90% of us selected options D and F, which are the correct answers as well. 90%, which is great. Okay. Now, just to bring everybody to the same page here again, which 2 options do we eliminate right away? Any? Thank you. A and B. Why do we do that? Yeah, because we are cooling, right? How do we know that we are cooling? Because we are starting over here at a high temperature, and then we are ending up at a lower temperature. The arrowhead indicates the end point, okay? Therefore, we must be cooling. If we are cooling, energy is released by the system. If the energy is released by the system, the change in energy must be less than 0. Okay. Therefore, our graph should be below 0. And that's the reason why we eliminated options A and B right away without even thinking. Okay. So A and B are out because we are cooling. Therefore, delta E is less than 0. And then between C and D, why did we eliminate C? Anybody? Why is C wrong? Yes, miss. I'm sorry. Remind me your name is one more time. Here's that. Okay. Yes, go ahead. I'm sorry. Thank you. If you are cooling, okay, we need to start at a high or low temperature. If you're cooling, we need to start at a higher temperature or lower temperature. Higher temperature and then end up at a lower temperature. But remember, when we start reading these graphs, we start at what point? Where do we start reading these graphs? At what point? How do we know the starting temperature? Okay, so in this case, it's the highest, but how do we know that that is the starting point? Yes, miss. Thank you. Because at the starting point, delta E, or the change in energy, is 0. Why? We haven't touched the system. There's no change in the energy of the system at that point. Okay, so delta E must be 0 at the starting point. And you'll see that in option C, our starting point is over here, okay, at a lower temperature. And then our end point is at a higher temperature. If we are cooling, this can never happen. Therefore, option C is out. Okay. On the other hand, in option D, we are starting at a higher temperature. Delta E0 is over here. And then we are ending up at a lower temperature. Based on that alone, this must be the correct curve. Okay. And then we can think about what is happening here. So we have a gas to begin with. We are cooling a gas over here. And then in this vertical line indicates gas becoming a liquid, a phase transition. The temperature remains constant. This is going to be the boiling point of this substance, whatever this is. Okay. And then we have this liquid, okay, cooling down. The temperature of the liquid decreases. And then we have a phase transition. This is going to be the liquid to solid phase transition. We call this as, anybody? Liquid to solid is called, what do we call that process? Liquid turn into a solid is called, thank you, freezing. Okay. And that happens at the melting temperature of the substance. Okay. And then let me mark that. And then once everything is converted to solid, and again, this ramp shows that, we are decreasing the temperature of the solid. All right. Do we have any questions, concerns, comments so far? Anything? Any questions, concerns, comments? Okay, so we're good here. 90% of us, got that anyway. I have a feeling that we are okay with that. Okay. Now, with that, let's try another one. I'm giving you 2 phase diagrams. Okay. What I want you to do is, in your groups, I want you to identify the differences between these 2. Go ahead. Diagrams. Okay. I'm going to go to my annotation tool, which is Zoom, which is very convenient to me. Okay. Anyway, so here's the thing. The question here, the questions are asking about the normal boiling point, condensation point, melting points, or whatever. Okay. What is meant by normal? Everybody. 1 atm. So what I do is whenever I, see that word normal, okay, I'm going to draw the 1 atm line in our phase diagram. So 1 atm for what is there, 1 atm for carbon dioxide is over here, something like that, okay? And then if I want to know the normal boiling temperature of, say, water, okay, we know boiling involves liquid becoming a gas. Therefore, that involves what boundary? Liquid gas boundary or solid liquid boundary? Everybody. Liquid gas boundary. Okay, boiling means liquid becoming a gas. Therefore, that should involve the liquid gas boundary. I see that my 1 atm line crosses the liquid gas boundary around that point. So if I draw a line back to the x-axis, that gives me the boiling temperature, the normal boiling temperature of the liquid, of the substance. Okay, that's how we find that. And if somebody asks you to do the normal melting temperature, you do the same thing. 1 atm line crosses the liquid solid boundary at this point. If you draw a line to the x-axis from that point, okay, and that temperature is the normal melting temperature of that substance. That's how we do that. Yeah? Any questions, concerns, comments so far? Okay. Now, if we try to do the same thing for carbon dioxide, all right, here's our 1 atm line. Okay, where's my mouse? Okay, here we go. Here's our 1 atm line. Okay, does it ever cross the liquid gas boundary? Everybody, can you look at that? Does the 1 atm line, okay, cross the liquid gas boundary of carbon dioxide? Never. It never does that, right? That means the normal boiling point of carbon dioxide, that means on the Earth's surface, is it defined? No, it is not defined because it is never going from liquid to gas phase on the Earth's surface. That's what it means. Okay, there's no normal boiling point for carbon dioxide on the Earth's surface. Maybe on a different planet where you have a higher pressure, there might be like 10 atm pressure. Okay, it might be the case, but not on the Earth. Okay, and then they're asking for the normal sublimation point, right, of carbon dioxide. You see that sublimation involves solid becoming a gas, that is the solid gas boundary. The 1 atm line crosses the solid gas boundary around this point. At that point, the temperature on the x-axis is minus 78. Therefore, the normal sublimation point of carbon dioxide is minus 78 degrees Celsius. All right. I'll give you 10 seconds to think about this, and then if you have any questions, I'll take them. Okay, let me see your answers as well, just for fun. Oh, no, I cannot do that. Here we go. Yeah, most of us got there, but not everybody. About 60% of us, identified there's no normal boiling of carbon dioxide on the Earth's surface. Okay, not everybody, but I'll reopen the question in case you want to revise your answers if you understand it. Meanwhile, do we have any questions, concerns, comments at the moment? Anything? Any questions, concerns, comments? Anything? Please, if you have any questions, chances are there are other people with the same questions as well. Please don't hold back. You can ask me questions, okay? All right, I'll leave that open. And then that brings us to the vapor pressure curves. Okay. So remember, the vapor pressure curve is the same liquid gas boundary on a phase diagram. Okay. Here what I'm doing is I am plotting the liquid gas boundary or the vapor pressure curve curves of two substances on the same plot. Okay, that's all I have done there. And based on that, I've given you 3 questions to answer. Go ahead. And it doesn't matter whether you notice or not notice the log scale. Okay, it is immaterial to this question. Volatile. Volatile means it easily goes from liquid to the gas phase. Okay, if a substance is more volatile, it's more easily or more readily goes from liquid to the gas phase than the other one. Yeah. 4, 3, 2, and 1. Oh, right. And maybe we can look at your responses. Let's see. Okay. Here are your responses for the most popular. Yeah, here are the responses for the first question. Which substance A or B is more volatile? Most of us said the substance A is more volatile. And that's the correct answer as well. Can somebody tell me why though? Why do you think substance A is more volatile? Why did you select that answer? Anybody? Yes, what did you select the answer? Yeah, why did you select that? I'm out of curiosity. Okay, that's true. Okay, so above the graph, above the line, we have the liquid. Below the line, we have the gas. But how do we know? How do we use that information to determine the volatility? Did I see your answer? Yeah, go ahead. Okay. So it reaches 1 atm at a lower temperature. Is that okay? That's a good way of looking at it too. Okay. So what's the name? Say one more time. Charlie. So what Charlie said was, if you look at A, all right. So let me draw that. Okay. So this is the 1 atm line, right? So substance A reaches 1 atm pressure, vapor pressure, at a very low temperature compared to the substance B. Substance B is around this much. That's good. That's a good observation. Okay. Now, anything else that we can consider to determine the volatility? Which one is more volatile? Yes? No? Okay. So here's what I would look at. Okay. So we know the vapor pressure gives us the vapor pressure of a liquid at any given temperature. Right? That's the definition of a vapor pressure. Done definition. That's the main information we are getting from the vapor pressure curves. You can see that at any given temperature, okay, let me go back. Okay, at any given temperature, the substance A has a higher vapor pressure than B. How do you know that? Let's go to minus 10 degrees Celsius. Okay, if you draw a line, okay, the vapor pressure at minus 10 degrees of substance A is this much. Okay, while that for substance B is this much. And around, say, 40 degrees Celsius, okay, again, let's draw this line, all right? Substance B has a vapor pressure of this much, and substance A is going to have a higher vapor pressure than that. Meaning, at any given temperature, substance A has a higher vapor pressure, meaning substance A goes to the vapor phase or the gas phase more easily than substance B, meaning substance A is more volatile than substance B. Okay. Again, the reason is at any given temperature, substance A has a higher vapor pressure based on the vapor pressure curves, and that's how we know that's why we know substance A is more volatile than B. All right, I'll give you 10 seconds to think about this. Okay, make your notes, and if you still have questions, I'll take them. Yeah. All right. All right. Do we have any questions, concerns, comments about this? Any questions, concerns, comments, anything? You have a question? Thank you. Where is it? Thank you, miss. Can you shout? Yeah. I mean, if a substance has a higher vapor pressure at a given temperature, that means that substance is more volatile. Okay, because how do we get a higher vapor pressure? More and more of it liquid particles go into the gas phase compared to the other one. Okay, and that's why it has a higher vapor pressure. That makes it more volatile. Yeah. All right. So the other question was, okay, let me clear my doodling for a second. Okay, the question was about the boiling temperature. Okay, which liquid do you expect to boil at a lower temperature? And then most of us answered option A, the substance A, as is going to go boil first at a lower temperature. Okay, and that is correct. Remember, the boiling occurs. When does the boiling occur again? Boiling occurs when, I know you know it. Boiling occurs when what happens? When what becomes equal to what? Come that again? It has to do with the vapor pressure and the external pressure. At the boiling point, what did we write in our notes? At the boiling point, vapor pressure is equal to what? Remember your names one more time. Diego. Yeah, go ahead. At the boiling point, vapor pressure is equal to? Yeah, external pressure, right? That's the idea there, right? At the boiling point, external pressure, the vapor pressure is equal to the external pressure. Now we know the external pressure is 1 atm, okay? So for substance A, so if I draw that line over here, okay? So here's the 1 atm line, okay? Substance A reaches 1 atm. We drew this before as well, okay? At a lower temperature, around 35 degrees or a little bit less than about 33 or something like that, degrees Celsius, while substance B reaches 1 atm or the external pressure around 78 degrees Celsius, okay? So which one boils first? Definitely at a lower temperature, definitely is going to be the more volatile substance, which is substance A, okay? All right. Do we have any questions, concerns, comments about this? Yes, Annie. Yes, absolutely. The more volatile substance will always boil at a lower temperature. Yes, yes. Any other questions, concerns, comments? Okay. Again, the idea is, okay, at the boiling point, vapor pressure equals to the external pressure, meaning the liquid particles actively go into the gas phase without a force. Okay. But I mean, at lower vapor pressures than that, you have the atmospheric pressure pressing on the liquid, not allowing the liquid to come to the gas phase easily. But at the boiling temperature, because they are equal at the boiling okay, because they are equal to each other, the pressures are equal to each other, you know, they are readily exchanged. They readily come into the gases. That's why the liquid boils at the boiling temperature. Okay. All right. Now, with that, let's do the last question. Okay, we spent a bit too much time there, but it's okay. The last question is, what is the normal condensation temperature of the more volatile liquid? And then, okay, so here's what we have. This is the answer, right? Like we have most of us saying around 30, 40, and then we have 35. Yeah, I feel like, I mean, it might be a little bit hard to determine that without, you know, having it on a paper or something like that. But anyway, so the more volatile liquid is liquid A or the substance A, okay? And then the boiling temperature of liquid A is around 35 or 34 degrees Celsius. Therefore, the condensation temperature, which is the opposite process, also happen at the same temperature. Therefore, the condensation temperature or the normal condensation temperature for that should be 35 degrees Celsius as well. Okay. Remember this, the opposite processes occur at the same temperature. For an example, okay, what's the freezing temperature of water? Freezing temperature of water is 0. What's the melting temperature of water? 0. Freezing and melting, opposite processes, they occur at the same temperature. What is the boiling temperature of water? 100. What's the condensation temperature of water? Again, 100. They occur at the same temperature. That's the idea. Okay, it is true for any substance. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions? Okay. So I think that should take care of that. Now I want to go back to what Teresa pointed out before. Okay. Now, again, just to remind us about this. Okay. So remember, this is coming from the phase diagrams. Okay. Pressure and temperature. So this is a phase diagram. Okay. And then the vapor pressure curve is actually the liquid gas boundary, maybe a part of the liquid gas boundary. That is it. This is the vapor pressure curve. Okay. Now, above this curve, what phase is dominant? What do we have above the curve? Liquid. And below the curve, gas. Do not forget that. Okay. I know that some of you already forgot that based on the first question I asked you. All right. Anyway, that's fine. So let's maybe 5 seconds. In 5, 4, 3, 2, and 1. All right. And then here are our responses. Most of us said option B is the correct answer. And then that's the correct one as well, which is beautiful. All right. One more time. Okay. So we are not given a pressure or anything like that. Okay. We are given the initial pressure, temperature and pressure. I mean, it doesn't mean anything. The question is asking without even giving the initial pressure and temperature. Okay. If you are given the wave pressure curves and if you are asked to determine the relative boiling points of the substances, okay, all you have to do is draw a line. Let's say that you are on, I don't know, like Jupiter or something where you have a higher pressure. Okay. So draw a line for the pressure. Okay. So substance A reaches the external pressure, that particular pressure around this temperature. For substance B is around this much. Okay. For substance C, it's around this much. I'm not reading the numbers for you. And substance D should, reach that around this much. Okay. You see that A boils at a lower temperature, and then B, and then C, and then D boils at the highest temperature, meaning the relative boiling temperatures, go from A to B to C to D. Okay. So D will have the highest boiling temperature out of all 4 substances. All right. Do we have any questions, concerns, comments? So the point is, it doesn't matter whether we are given the pressure for this question or not. Okay. At any given pressure, you see that substance A reaches that external pressure at the lowest temperature, and substance D reaches that external pressure at the highest temperature. That's the idea. That's the ranking or the relative boiling points of these substances. All right. Do we have any questions, concerns, comments, anything? All right. One more thing. I think 2 more things with that. Then we're done. All right. Let's do this question. I think this is the same question I gave you at the beginning of the class. All right. Some of us might have to revise some answers. Okay. If that is the case, that's okay. Correct answer. Now, the first thing you need to do when you're given a question like this is mark the point. Okay, your initial conditions are given here, 5 degrees Celsius and 1 atm. It's given in the question as well. So this is 0. 5 degrees must be over here and 1 atm line is over here. That will put me just below the B wave pressure curve. Okay. Now we know based on what we just discussed, here's a wave pressure curve, pressure and temperature. Okay. And if you are below the wave pressure curve, what's your phase? Yeah, you should be in the gas phase. If you're above the wave pressure curve, you're a liquid. That's the idea now. Now, this point is where you are now. Okay, here's this point. Now, this point is below the wave pressure curve of B. If that is the case, B must be in what phase? Thank you. B must be in the gas phase, right? So B is in the gas phase for sure. And then definitely this point is below the wave pressure curve of A. Therefore, what should be the phase of A? If you're below the curve, what's your phase? Gas. Therefore, A must be in the gas phase as well. Now, this point over here is above the wave pressure curve of C. If you're above the curve, what should be your phase? If you're like here, what should be your phase? Everybody, if you're above the line, what's your phase? Yeah, you're a liquid. Okay. And then definitely D, so with respect to D, you're above the line of D. If you're above the line of D, what's your phase? Yeah, again, liquid. Okay. Again, only thing to remember here is if you're above the line, you're a liquid. If you're below the line, you're a gas. That's all you had to remember there to get this right. Okay. And these are our phases, and this is the most popular answer as well. I'll give you 10 seconds to think about this, and then I'll take any questions you might have. Go ahead. Discuss with each other and make sure that we understand this.
You said that above the line is liquid, but those two are below the line. Wait, okay, hold on. You said above the line is liquid, but then you wrote gas for A and B.
Yes.
So now I'm just...
Because So forget about all the lines except for line A, yes?
Yeah.
Okay. And your point is below the line of A now.
Yeah.
If you're below the line, what's
so
your phase?
where it is relative to that specific
Yeah,
line.
you look at where you are with respect to that line. Okay.
Thank you.
Yeah, absolutely. That's a common question, Jay. I know that there are a lot of other people had the same question, but they did not have the guts to answer that. Okay. So please, I welcome your questions. Okay. Again, you look at where you are with respect to the line because you cannot change the line. You can change where you are. If you want to change the world, you change yourself. Okay. Right. And you want to separate A from a mixture of A, B, and C. Go ahead. What would you do? By the way, I have now, you know what? Before I look at your answers, let's think about this for a second, okay? So we're trying to separate A from like everything else. That's the goal, right? So anyway, so let's identify some regions in the phase diagram here. So here's my region, I don't know, let's say X, Y, Z. I want to come back to A, maybe Z1. Anyway, that's okay. Now, if you want to separate A from everything else, what region do you want to be in? Like X, Y, Z, or Z1? Thank you. You want to be in this region over here. Okay? It doesn't matter where you start at, as long as you end up in that region, you achieve a separation. You separate A from everything else. Why? At that point, A is below. So if you're in that region, okay, so A will be in the gas phase while the other substances are in the liquid phase. That's the goal there, okay, to have your substance in a different phase than the other one that you want to separate. Okay, that's the idea. Now, anyway, so to do that, we are starting around at 180 M and 300 Kelvin. 300 Kelvin is 27 degrees Celsius, which is going to put us over here. Okay. So you can achieve that by maintaining the same temperature, but increasing the pressure like this, or maintaining the same pressure and decreasing the temperature up to this point like this, or decreasing temperature and increasing the pressure like this. So those are the ways of achieving separation or to entering the Y region to separate A from everything else. That's the idea. And how many ways did you figure out? You know what? Let me open the question again in case you want to revise your answers. Then we'll look at your answers. All right. I'm going to look at your answers in 5, 4, 3, 2, and 1. And here are our responses. Okay. Most of us said option B. Okay. Increasing the pressure to 8 atm while holding the temperature constant, meaning like going up like this. Okay. So holding the same temperature means you are going vertically up. Okay. Increasing the pressure to 8 atm. That will work. And increasing the pressure to 5 atm and decreasing the pressure to 10 centigrades. Okay. So 10 centigrades and 5 atm would be somewhere around here. Again, that will put us in region Y. And then the other ones, definitely B and C are the correct answers. Okay. And if you look at the other ones like C, increasing the temperature to 70 degrees, maintaining the same pressure will be a wrong answer. Why? Because that would take us, let me use a different color. Okay. That would take us over here. Right? That will not achieve the separation. And then the last wrong answer is option D, decreasing the pressure to 0.6 atm while holding the same temperature. So that means you are going down this way. Okay. That will not get us region Y. Therefore, that is out as well. All right. Do we have any questions, concerns, comments about this? Anything? All right. This is how we play with the wave pressure curves, especially when it comes to separating substances. Any questions, concerns, comments? Anything? Okay, so that's it for Unit 1, Module 1. Okay, I'm going to give you a preview of coming attractions when it comes to Unit 1, Module 2. All right. And just to remind us about what we are doing in Unit 1, Module 2, we are trying to, let me reopen this as well in case somebody wants to revise the answers. But by the way, I'm reopening all these questions after class for 24 hours. This will be available until 11:59 p.m. tomorrow in case you want to go back and revise your answers. Okay. Hope I did something weird. Okay. Anyway, so that's the idea. Now, in Unit 1, Module 2, what we are trying to do is to explain the differences we identified in Unit 1, Module 1. Now, whenever the scientists are asked to explain something, okay, they do something. What do they do? Anybody? How do they explain things? They're going to do experiments, okay? So before the experiment, they're going to come up with something else. They're going to come up with, okay, to do that, you need, before that, you want something else. Hypothesis or a model. Okay? They always use models to explain things. Okay, so that's what the scientists do. Okay, you're going to be doing the same thing as scientists. All right. Now, anyway, so what we're going to do in Unit 1, Module 2 is we're going to use a model called, anybody who read the textbook? The model is called, nobody read the textbook yet. It's due tomorrow. Thank you. I heard that. Particulate model of matter. Okay, is the model we'll be using to explain the differences we saw in Unit 1, Module 1. That's the goal. Okay. Now, anyway, when it comes to models, the models are based on what? When it comes to any model, a model is based on any ideas? What did you say again? Sometimes math, okay, but even in math, okay, what do we do to come up with models? We need to have, yes, Annie? Okay, so that's what we use the models for, to explain and predict. Okay, but to come up with the model, we need something bad, actually, in a way. We need, yes, sir. Okay, we use the models to explain the data. Yes, miss? Theory or assumptions, right? We need all the models are based on assumptions. Okay, we're going to come back to this like time and again, okay? Because models are based on assumptions, okay? And the particulate model of matter also has 3 assumptions in it, okay? What we are doing in Unit 1, Module 3 is going over these 3 assumptions, and that's it. That's all we do there. Anyway, does anybody know, anybody have any guesses about the first assumption of the particulate model of matter? What do we assume first in the particulate model of matter? The matter is made of, come that again? Matter is made of, particulate model of matter. I think I heard that. Thank you. Particles, right? Matter is made of particles. That's it. Okay. That's the first assumption of the particulate model of matter. Matter is made of particles. Okay. Now, not just one particle, by the way, we are talking about, okay, a large number of small particles. Okay, so matter is made of large number of small particles. Even if you forgot about the large number and then the small particles, if you can remember that the matter is made of particles is the first assumption, that would be great. But I will never ask you to write the assumptions of this model in an exam or something like that, because that would be a boring question. Okay, I'm not going to do that. There are more exciting things to do. All right, anyway, so now, what do I mean by a large number? Okay, if you, to give you an example, if you take 1 milliliter of water, like 1/5 of a teaspoon of water, okay, that contains 3.34 times 10 to the power of 22 particles of water. That's a huge number. Okay, that's how large number when I say large. Okay, large the number is when I say large. Okay, and then I also said very small. And this is not scientific when I say very small, okay? Like, you know, so we're going to be a little bit more scientific here by giving you some scale. So this is 1 meter, okay? And then this is like 10 centimeters, okay? 1 centimeter, okay? And then 1 millimeter, you can start seeing the cracks on the skin now. When you zoom in further, okay? Like 10 to the power of minus 5 meters, you start seeing like the large cells on your skin, okay? And then zoom in further, 10 to the power of minus 7 meters, you start seeing the larger molecules like DNA and protein at that level. But when I say very small particles, I mean 10 to the power of minus 9 meters. And this happens to be the nanometer scale, okay? So if you know this conversion, that would be great because, okay, we come across nano, like, a lot of times, like nanobots, nano machines, nano technology, So when we mean nano, what is meant by that is like 10 to the power of minus 9. That's the idea there, okay? So that's the scale. That's how small the particles we are considering in the particular bundle of matter. All right. That's assumption 1 for you. Do we have any questions, concerns, comments? Okay. Now, again, the first assumption of the particular model of matter is made of particles. That's it. Okay. Now, just to be careful here. So now this is how we can represent a solid, liquid, and gas here. Does anybody notice the main difference between the three phases in the particular model of matter? What's the main difference? Thank you. The space between the particles, or the distance between the particles, right? So you have in a solid particles closest to each other, which is arranged like in an organized manner. And in a liquid, particles are not as close to each other as in a solid, okay, but they are closer than in a gas. And they are more random now, okay? They have more freedom to move around. They're more random in a liquid. But when it comes to a gas, the particles are furthest apart from each other, okay? And they are extremely random. All right, and this is how we represent the three phases using the particular model of matter. And also, these particles can be atoms, molecules, ions, depending on what we are trying to represent. And also, even though we draw like static images of these representations, you have to remember, these are not static. These particles are never static. They actually move constantly in random directions. Okay, they move all the time. That's it. Okay, and in fact, that is our second assumption of the model. Okay, so number 1, matter is made of particles. Number 2, these particles move. Okay, these particles move. That's assumption 2 of the particular model of matter. I mean, it seems pretty like primitive, like these assumptions, but I mean, you're gonna find out that you can do like much advanced things with this. Okay, so again, assumption 2 says that these particles move constantly, or in other words, all the time, in random directions. That's what assumption 2 says. Okay, and this is a simulation of the particular model of matter, like a model of a gas. Okay, so I'm going to show you some. I'm going to start the simulation now. Okay, and then you're not going to see a picture like this. Okay, in the particles in the matter is going to be moving all the time like this. Do we have a question now? Do we have any questions, concerns, comments at the moment? Anything? All right. Now, let's get a little bit serious here. Okay. Now, these particles, do they all move at the same speed, or do they move at different speeds? Don't answer this. Okay. Think about in your groups. Okay. Look at, just make that observation based on the simulation I'm showing you, and then answer this question on top hat. Go ahead. All right. Let's see how we did. Okay. And here are our responses. Most of us observed, more than 90% of us observed that these particles are moving at varying speeds. Yeah. So some of us saw the same thing, but came up with a different conclusion, but that's okay. That happens. But anyway, so at least most of us agree that these particles move at like different speeds. Okay. So the idea here is, if I draw something here, let me see if I can do it. Okay. So let's do this. Okay. So if I have the speed of the particles on the x-axis, speed. Okay. And then if I have the fraction of particles on the y-axis. Fraction means it's like the percentage of particles. If you have 100 particles, how many particles move at a certain speed? That gives you the percentage, okay? But in fraction, instead of having 100 in the denominator, we have 1. It's the same idea though, okay? Fraction and percentage, they are analogous to each other. Okay, anyway, so what we just discovered was, based on our observation, we have a distribution of speeds like that. Okay, and then most of the particles will be moving at a speed around here. It's going to be our average speed, okay? But at the same time, there will be some particles moving more slowly, and some particles will be moving faster than the average speed. That's the idea. All right. Do we have any questions, concerns, comments? Okay, so we have a distribution of speeds. Okay, this is kind of important in a way. Okay, even just this explains the phenomenon called evaporation. Okay, example, what happens in evaporation? Okay, these particles that have a higher speed. Let me do this here so that it is it's gonna make things connected. Okay, the particles with the higher speed, that is the particles over here, can escape the attractive interactions in the liquid phase and then go into the gas phase. Okay, and that is what is happening in the evaporation, and that happens at any temperature, even at lower temperatures than boiling temperature. Okay, so this distribution of speeds according to the particular model of matter can be used to explain the evaporation, which was something we discussed in Unit 1, Module 1. Yeah, go back to our simulation for a second.
It's gone.
Okay, I'm going to keep my drawing here for a second because we're going to need that. Okay, now here's another observation I want you to make. Okay, what I'm going to do now is I'm going to change the temperature of the system using the temperature bar here. Okay, now please pay attention now. Now I'm starting at a lower temperature. What I'm going to do is I'm going to increase the temperature. Okay, then I'm going to decrease the temperature. One more time. Increase temperature. Decrease temperature. All right. What did you notice? When I increase the temperature, what happened to the particles? They move faster, right? They move faster when I increase the temperature. In other words, if somebody twists your arm and asks you to define the temperature based on the particular model of matter, how would you define it? Okay, let me start. Temperature is a measure of what? I'll give you a second in your groups. Go ahead. Okay. How would you define temperature based on the particular model of matter? Temperature is a measure of, go ahead, the moving objects or moving particles. Okay. So what Cole said was, when you increase the temperature, we see that the particles are moving faster, meaning particles must have a higher kinetic energy when they at higher temperatures than at lower temperatures. Yeah. So in other words, temperature is a measure of here's the keyword though, the average kinetic energy per particle. Okay. Let's make a small note if we can. This is really important. Okay. So see if I can do this here. So temperature okay, is a measure of the average kinetic energy per particle. Even if you forgot the per particle part, it's not the end of the world. Okay, if you can remember that the temperature is a measure of the kinetic energy, average kinetic energy, okay, that would suffice. Okay. Do we have any questions, concerns, comments so far? Okay. Okay. All right. And then again, what we notice is if we represent the same observation in our like a distribution graph over here. Okay. So this is our lower temperature. Okay, this is our T1, which is the lower temperature, okay, indicated by blue for ice cold or blue, okay, whatever, lower temperature. And then what I'm going to do is I'm going to draw the distribution of particles at a higher temperature too. At a higher temperature, this distribution will change like this. Okay, so what happened here at higher temperatures? The average speed or the average speed for the particle has moved from a lower speed to a higher speed. So now the average speed is somewhere around over here. Okay, and then T2 is greater than T1. That's the idea. Red is for the higher temperature, and blue is for the lower temperature. Okay. All right. That's why we have more vapor pressure at higher temperatures. Why? There are more particles with higher speed. Okay, and those particles can escape into the gas phase more readily. That's why we have a higher vapor pressure at higher temperatures. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? Okay. So I'm just giving you a preview of coming attractions. You see that we only use two assumptions so far, two primitive assumptions. Okay. One, the matter is made of particles. Two, these particles move constantly in random directions. That's all we did. But with that, we were able to explain evaporation process. That's it. Okay, that's how beautiful this process is. You know, that beautiful and powerful this model is. Anyway, I'm going to keep this here for the moment. Okay, I have 2 more minutes. Give me a second. All right. So I did that. All right. This is again in a same way. Okay, so kinetic, and so assumption 2, the particles move constantly in random directions. So with that, we define temperature as the measure of the average kinetic energy per particle. Okay. Now, here's the last question we're going to do today. Let's think about water at its triple point. What I want you to do is, I want you to determine the answers to these 2 questions. Go ahead. I'll think about it. I'll come back. Yeah, because we're running out of time. Yeah. All right. So because we are running out of time, please submit your answers. Okay, 10 more seconds. Please submit your answers. Okay, so they are all at the same temperature, meaning they should all have the same what? I like it. Same average kinetic energy. The key word is the average. Okay, so they are all at the same temperature, meaning they all have the same average kinetic energy. Okay. And then we know from physics 101 or something like that, kinetic energy is equal to half mv squared, right? Okay. So they all have the same kinetic energy. They all have the same mass because we are talking about the same water particles here. If that is the case, what can you tell me about the speed? By the way, m here is the mass, v here is the speed. Okay. If they all have the same average kinetic energy, what can you tell me about the average speed? They should be what? Thank you. They should be the same as well. Okay. So regardless of the phase, okay, if the temperature is the same, they should all have the same average kinetic energy and the same average speed. All right. So the keyword is average here. All right. We'll continue this on Thursday. Bye, everybody.